Example number 6 in our rotational dynamics, we have 4 rotating masses, 3 kilogram, 2 kilogram, 4 kilogram, and another 2 kilogram. And they are rotating along this XY plane. So it's basically spinning around in this direction. So in the plane of the page or the screen that you're looking at. And we're asked to determine the moment of inertia about the z-axis, which is going through this. If you can imagine that there's an axis that is coming straight out of the screen towards you. And it's rotating at an angular velocity of 6 radians per second. So that's omega. Omega is 6 rads per second. And what we need to do is determine, first of all, the moment of inertia. So the moment of inertia for masses that are away from a certain origin is basically using this formula. It's the sum of mi times ri squared for all the different masses. So we're going to be adding up all the individual masses. So we'll just simply call this m1. We'll call that m2. We'll call the 4 kilogram one m3, and the last 2 kilogram one we'll call that m4. Now r in this case is the distance from the axes of rotation to each of the individual masses. And in this case, because it's a nice symmetric problem, we're just going to be figuring out the distance here from one center to the middle of this, because this rectangle is perfectly centered along the axes. At least that looks what it looks like. 6 meters here, so that means it's 3 meters up here, and then 4 meters across, so this is 2 and 2 in here. So r is this distance right from here to here. That's what we need to figure out first. All right, so r is going to be equal to the square root of, because we're going to use Pythagorean theorem, and this side over here is 3, and this side over here is 2. So it's the square root of 3 squared plus 2 squared, which is root 13 meters. I'm not going to convert that to decimal because I'm going to be using it in this formula in a second anyway. So now we can go ahead and use it in our formula. m1 r squared plus m2 times r squared plus m3 times r squared plus m4 times r squared. And we're simply going to add them all up. So I will be equal to, well, I guess we could just do a common denominator of r squared out. So it's going to be really root 13 quantity squared multiplied by 3 plus 2 plus 4 plus another 2. And if you calculate that in your calculator, it should come out to roughly 143 kilograms times meters squared. That's part A. Okay, so that's the moment of inertia, or the rotational inertia of this 4 rotating masses rotating amongst this plane. Now I could figure out a different rotational inertia. If I were to say have it rotate along this y-axis, then it would be different, because their distances would be, say, 2 and 2 for this one, and we would have a different radius from the center of axes. But anyway, for this particular problem, this is a rotational axis right through the center of your screen. B part, we're looking for the rotational kinetic energy. So if you recall earlier in the notes, we introduced the rotational kinetic energy formula. That's equal to 1/2 times the rotational inertia multiplied by the angular velocity squared. So we're going to be using the total rotational inertia. That's what we just figured out for this system. So that would be 143 kilograms times meters squared multiplied by the angular velocity, which is given as 6 rads per second, and that is being squared. And that gets us a rotational kinetic energy of 2,574 joules. And that's it for example number 6.